So last time we looked at a system which was just a particle. And what we were doing in that case was just how to describe a particle, what kind of answers, what kind of questions we can ask. So essentially, we found that for a particle, there are some systems in quantum mechanics which are considered to be quantization of classical systems. Not all of the systems have to come to that, but many of them are, so that you have a classical analog of the system, and then when you treat them quantum mechanically, you have some kind of a correspondence between those two things, and the classical picture emerges only in certain limit. So in a sense, quantization gives you a much better picture of the system, what we call a quantum mechanical picture. So a particle should be thought of quantization of your usual classical conception of a particle, where you have momentum and position. You have these to describe a particle. We found out, like as per our postulates, we won't be describing our system, which is in this case is a particle, will not be described by giving a position and momentum, because that's not at all what the postulates say. Is described by giving a state vector corresponding to position and momentum, because position and momenta are observables. We have instead operators which can act on the Hilbert space where your all possible states live. You can look at this state in the position basis. Position basis is available to us because in this Hilbert space we have this guy x hat operator acting. So its eigenvectors form a basis, since it's a Hermitian operator with the appropriate boundary conditions in this Hilbert space. It's a Hermitian operator, and these vectors form a basis, so I can resolve in this basis. So this should be thought of, this wave function, as a picture. I shouldn't use the word picture because picture I'll be using for something else. It's just a representation of the state. So if you are writing a wave function, you are describing the state completely because you are giving all its components in a particular basis. So this is how the particle is described. Particle's complete description. And then as per our postulates, we saw that how will we find, what do we mean by that the particle has a certain position and momentum? Well, we found that there's no meaning in saying that it has a certain position and momentum. All you can talk about is having the probability of position equal to some value, and around it between, let's say, x naught and x naught, and this was proportional to this wave function evaluated at that position where you want to find the probability mod square. And similarly, you can find the probabilities for momentum equal to certain value p naught and delta p. That was computed by taking the Fourier transform, going to momentum space, and something like that. So you can only talk about the probabilities of having a certain position and certain momenta. And we found that we cannot so since it's a probability, so you have a probability distribution for position, and you will have a corresponding probability distribution for momenta. And as you pinch one, the other one gets broadened. So there is this, there will be uncertainties because of the probabilities coming into pictures. So you won't be able to predict that what will be the position when you measure this. When you try to measure the position of this particle, what it would be, you won't be able to predict. You will all at maximum be able to predict what is the probability distribution. If you try to find the position on identical particles, all of which are in the same state. So that's the point. You know the system completely. You have specified it completely. You take a trillion, let's say a million particles all in the same state. But all of them, when you measure, they give you a different position. Because position is only probabilistically defined, you only have a probability distribution for it. You have complete knowledge as much as the theory allows you, but based on that, you cannot predict what would be the position. Since you cannot predict, no one can predict, so it's kind of useless to say that what is the position of the particle. All you say that it has a wave function, and the wave function has the information about the probabilities of position and momenta. And you can have different states. In different states, the probability distribution. What is the purpose of this wave function? The wave function, since it has all the information about the particle, and that information is actually gives you the probability distribution for all possible observables. They're all contained in it. And if you change a wave function, that means if you put the particle in a different state, your probability distribution which you get changes. So the probability distributions, they are a function of your wave function. And it turns out that if you create such states which have a peaked probability distribution for position, then they will have a broader probability distribution for momenta. And this was the relation we found, that the product would always be greater than or equal to h bar over 2. So that Gaussian which we were studying, this kind of a wave function, e minus ax square, this is just one example of a wave function. One should, since it's used a lot, one should not ever try to think that the particle can only live in this wave function. There are essentially no kind of no restrictions that what kind of wave function you can have. We will see some restrictions which we need, but essentially it could be any arbitrary function. This is fine. So this wave function has probability to be found here, 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 but not here. And I'm only drawing some part of it, either the real part or the mod square, because the actual state is described through a complex wave function, complex function. The only thing so far what we need is that this wave function belongs to the Hilbert space. And we found out that for the Hilbert space where these guys are included, you have only the restriction. Your restriction is that the wave function at infinity goes to 0. As x goes to infinity, plus or minus. Why? Because you want them to be square integrable. That's how you have defined your Hilbert space. This is less than infinity. That will only happen if this wave function goes to 0 at infinity. So within this square integrable space, you can define your hermicity and everything. So this is the one condition you have. But this, we found that this is too restrictive. That's not all the wave function you throw in your Hilbert space. You can also have the delta functions, which should actually be thought of as some kind of a limit of a broader peak. Probably if I want to be very mathematically minded and just work with the L2 space, which is this space of all the square integrable functions, then I won't be throwing in the delta functions. They will be like something which look very close to delta, but I just take the limit and I say, just to work quickly with my calculations, I throw in deltas. Also, there are some functions, only one class of functions, which do not go to, some wave functions are allowed, for which this does not hold. And we had discussed that these are only these exponentials for any real k. So these are allowed. These are not square integrable. If I make these mod square, I don't know how to take the limit, but these are allowed. So they don't go to 0. They are just plane waves. Even if you go at infinity, they look like plane waves. So these are allowed. These you throw in. And if you want, you can also think of them as some kind of idealized wave that in principle at infinity you taper it off. So it's like a e to the iota kx for a very large range, but at very, very far away distance from your region of interest. When you go out of this region, you can taper it off so that the true function is not e to the iota kx, is e to the iota kx in some region, and then it goes to 0 beyond that. But obviously, if I, so that you can call putting the wave function in some kind of a range. People call it putting it in a box. But dealing with it all the time becomes very cumbersome. So you just throw in these kind of guys which keep going, which are true exponentials. And we had discussed in detail that if I take this k to be real, then I know how to define Hermitian operators. Everything stays Hermitian, so I can consider them as part of my Hilbert space. With this thing in, I have this representation of the momentum operator in the position basis, and this then becomes the position basis representation of the eigenvectors of P. And it turns out that if I include these, P is a Hermitian operator if I take the limit properly. And because of including this, I have the eigenvectors of P. If I don't include them, I won't have any eigenvectors of P. In the abstract theory of, in the proper theory behind quantum mechanics, the operator theory, which was discovered by von Neumann, the operators do not have to have eigenvectors. You can still describe the spectrum without having eigenvectors, but that becomes way too technical for our purposes. So we just put in these guys, and these are also part. So the point I was making, that Gaussians are not the only state. Even if I draw them many times, wave function can take any form, as long as it goes to 0 at infinity, or it looks like this guy, or a delta function. These three possibilities. Any function that goes to 0, at infinity, and it's continuous or whatever, as long as you have this condition that the integral gives you a finite number, or it goes like this. So with this thing, you can see that if I have a function which goes to 0 at x going to plus minus infinity, then I can normalize it, because this is going to give me, because it goes to 0 at infinity, so it's going to give me some number, let's say alpha, let's say alpha square. So I can normalize psi of x like this, and you can include a phase if you want. So this new one mod square will have the mod square integral equal to 1, and that we know implies that the total probability of finding the particle in what range, in any range, in any, on any position from minus infinity to infinity, anywhere, is equal to 1, as it should be. The particle is somewhere, so it's on the real line. I'm just considering one dimension, so the total probability should sum to 1. But this kind of thing you cannot do for this. If you have this wave function, if your particle is described by this, what can you say about this wave function if the particle is described by this? Let's call it psi k of x. One thing you can say, that you know the momentum completely. What is the momentum? Because it's an eigenstate. Because it is an eigenstate of the momentum of this operator. So if you are in an eigenstate of an operator, then you know with certainty what is the going to be the outcome if you measure that observable. So since it's an eigenstate of momentum, you know exactly that what is its momentum. It's some fixed value h by k. But as for position, and it's also coming from because of this relation. But since the wave function looks like this, and when I make the mod square, that's just 1, I cannot normalize it. It's everywhere it's taking the same value. So when I, even if I multiply it with any constant, psi k mod square would be constant mod square. So when I integrate it, it gives me a mod square times infinity. So no choice of a, unless I put it 0, then I don't have a wave function, will give me a finite value. That means I cannot choose a constant to give me a total probability equal to 1. I cannot use, you say that you cannot normalize this kind of wave function. Wave function cannot be normalized. But it doesn't bother us, because we know that why it's not normalized. All it's saying, this statement just means that there's equal probability. We have maximum uncertainty about position. There's equal probability of it being anywhere. We have no knowledge of position, because we have complete knowledge of momentum. And that's all this statement means, that it cannot be normalized. the real wave functions, if you take any real electron and you say that it has a momentum, you say that this electron has a particular momentum, let's say 3.567, some value, then that would mean that there will be a corresponding k, which you compute like that, and you can draw a wave. But the real electron, in most conceivable circumstances, will be contained in certain region. So you can say like it's in this room. So that means, truly speaking, its wave function will not be this. Its wave function would be like this in a big range, but then it taper off. So like at the walls of the room, it becomes kind of zero. So you have no probability of finding it outside the room. So that means your delta x, so you have, let's say, equal probability of being found anywhere here. So your total uncertainty of it being, total uncertainty would be the standard deviation where it can be found. So it would be the length of your room. So your delta P would be h bar over L. Now, since this h bar is very small, in those units where, let's say, if I take 1 meter, then h bar is 10 to the minus 34 joules second. So this uncertainty becomes, in momentum, becomes very, very small. But there is uncertainty. But as soon as you have an uncertainty in momentum, you know that you do not have a true exponential, a true pure wave. But for practical purposes, because a true wave must have exactly one wave number, it should not have any uncertainty in what wave numbers you are considering. So, but from a practical point of view, you can take it to be a pure wave because the uncertainty is so small. So this fact that these wave functions cannot be normalized is just for our mathematical convenience. Real electrons, real particles, they don't have these kinds of wave function, because at some point you will have, you can, like, maybe even if something has a very exact momentum at the like end of the Milky Way, you may know that it is within this region of the galaxy or in this region of the universe. So at some point you can cut it off. And so there are no true exponential functions, but they are very, very convenient. Practically speaking, you can replace your many of these cutoff kind of wave functions with these kind of pure wave functions. And how do you interpret it? You just say that whenever I have this wave function, then I know the momentum. And I don't know the position. So any question? Now let me talk about, so we had discussed the particle, but we hadn't described its dynamics. That how does this particle's state evolves with time. But we have discussed all that in general, and we just have to adopt it here. So you have, we know that the dynamics of the particle. When you say dynamics means that how does the state changes. We know that this is described by giving a Hamiltonian. So what would be the Hamiltonian of a particle? Well, the prescription is that the Hamiltonian you construct by taking the, for most cases, we are not really going into very detail. I'll probably do it towards the end of the course, that how exactly when you are quantizing a system, how do you derive a Hamiltonian? Because to do that, you need to know a little bit of classical mechanics at an abstract level. Probably I'll do it someday. But for most simple systems, all you do is you take the energy expression for your particle. So if this is your energy, and you replace every quantity, energy will involve momenta and position. Position because you will have a potential. For the particle. Potential or potential energy. And this is the kinetic energy. So Hamiltonian for most simple cases is just kinetic energy plus potential energy. So this is like total energy. But these are just classical expression. You need an operator which acts in your Hilbert space. So that you just get by replacing everything with their corresponding operators. So P becomes, the momentum becomes the operator for the momentum. And this potential, which is a function of position, becomes the function of the operator x. So you can think of it, whatever functional form you have for v of x, you can probably expand it as a power series. And you replace all these terms. You have some powers of x. So you replace all those terms by the operators for x. So that's how you will get the Hamiltonian. So a particle, classically speaking, its dynamics depends on what kind of forces are acting on it. What is the force on it? Depending on force, it behaves differently. So in quantum mechanical case, that effect is captured through this. So you can see that this factor, this is the kinetic energy, it will always be there. Whatever, if you have, every particle has a momentum. So it always has a kinetic energy which is equal to p squared over 2m. That gets replaced by a kinetic energy operator. But this potential operator will be different for different forces acting on the particle. Because I know that in classical mechanics, I can write the forces like this. So the force is somehow related to the potential energy. When you do quantum mechanics, you cannot deal with forces. There's no concept of force in quantum mechanics. You cannot describe the dynamics using a force. So you describe it using this V. So you have a correspondence, there's a correspondence with classical mechanics, with classical systems. If classically you are describing, you want to describe a certain kind of force, let's say you say that I have applied electric fields, you have to pick up corresponding potential which gives you that force. You can't deal with the force directly. You find out the potential which gives you that force, and you put that potential over here to get your Hamiltonian. And it's the Hamiltonian in quantum case which will govern your dynamics. So a particle is not just one system. A particle, people talk of different systems whenever you are considering different forces, or whenever you are considering different potentials here. So for every potential, you kind of think of it as a new system, because each one of them has different dynamics. What we had described before was without any dynamics. Just like at this moment, if I catch if I observe the particle, it has a certain wave function. What happens if I measure things? I didn't describe if I start with this wave function, what happens to it at later times. So for that, you need a potential, and from that you construct the Hamiltonian, and that gives you the dynamics. Now, what is the simplest potential you can consider? Can you give me some suggestion? So I want to consider a simplest system, and I have to give a force and correspondingly a potential. So what simplest system you can think of? कोई बोल नहीं रहा? Sameen? क्या simplest system? What simplest system you can think of?
सर किसी हाइट पे जब पोटेंशियल ले लेते थे mgh तो वो सिंपलेस्ट मेरा ख्याल है वही नहीं होगा usually we
Okay,
consider that
okay, that could be one. किसी और के पास कोई और idea?
Sir, potential energy 0.
Yeah, that's even simpler. Potential energy is 0. So the force is 0. It doesn't have to be 0. You can just say a constant, but we will see that constant can always be absorbed. Constant doesn't do anything, not much. So I can change the constant and bring it to 0. But if the potential energy is constant like that, then dv over dx is 0. That means no forces. So it's a free particle. So particle moving in space, empty space, there's nothing around it, no forces. So that's the first system, first dynamics we want to consider. I'll not go into much detail, at least I will not do the calculations because I did the calculations last time. They are very, very similar, but let me just talk about some concepts. So we know that solving the dynamics, we had discussed it, is essentially equal to solving the eigenvalue problem for the Hamiltonian. Because if you have these eigenfunctions, all the eigenfunctions, then they will form the basis, and you can use them to evolve any state. Well, we had actually did this, that this operator, the evolution operator, is just this. The issue is that you want to apply it on a general state. If you have solved, so you get psi of t from psi of 0 by applying this. How do you apply it? If you had solved the eigenvalue problem, then this x here, this is just a revision, we had done it. This is just a number. You have solved this problem, so you can compute it. And this sum gives you the function at a later time. So that's the idea. I'll do it in a few different ways. First of all, let's see what are the Eigen functions. Well, I observe, and the Eigen functions, all the Eigen functions are going to form a basis. This, with all different k's, is a basis. And fortunately, in this case, it's an eigenbasis of H. Because what is H? H is P square over 2m, which is H bar square K hat operator square over 2m acting on K. And K hat operator has these guys as the eigenvectors. So this K basis is an AG eigenbasis. But only for free particles. And there's just a little interesting thing to note that this guy has this energy. Let's call it EK. Define it like this. Then this guy with the opposite, because K's take value from minus to plus infinity, with the opposite sign, it also has the same energy. E of minus K is equal to E of K. It has different momenta. Momentum of this guy is H bar K, and momentum of this guy is minus H bar K. So they are like describing, these states are describing a particle moving to the right. This is K, let's say, with a certain momentum P, while minus K state is describing a particle moving towards the left, but with same momenta. And as you expect that the energy, it's the square of it doesn't depend on which way the particle is moving, it's just the kinetic energy. So you get same value for the right and left movers. And so you say that energy eigenvalues are doubly degenerate. That is just terminology. We had said that many a times we will encounter operators whose eigenvalues will be degenerate. So that means you will have same eigenvalue, you will have more than one eigenvector with same eigenvalue. But, and in that case, we were looking for that, so this is a two-dimensional subspace. And in this case, we know that it is being spanned by this. Whenever you have such a situation, you look for those vectors which are orthogonal. But in this case, because by definition, these guys are with different k's are all orthogonal in this sense. So we don't have to do anything. We already have an orthogonal basis, so we are good to go. Don't need to do any extra work to make these eigenvectors orthogonal to each other. First, so when you get into this situation, usually what you want to do is get an orthogonal basis, but we already have it in this case. So now one thing you can do, you have a state and you want to evolve it. I'll describe this evolution evolution in position basis. You can do it in momentum basis as well, doesn't matter. That means I have this guy. This is the position basis representation. I have the wave function. So I want to know that what happens to this wave function if I start with t is equal to 0 as psi of x. What happens after a certain time? So this you can obviously do this way. If well, this by definition is psi at a time, later time t. And I can look at it by projecting it onto position basis. Wait, just wait a second, let me take a call. So this is, so you have the wave, the state at a later time, you project it onto x. So this is the psi of xt, the components of the state at a later time. Or in common language, you say that the wave function at later time t. So how do you find it? This is just x acting on this. And I can include now an identity h bar x dash, and this is psi of x dash. So this becomes kind of a kernel. It has two arguments, x and x dash. So you can call it, I'm just giving it a name, x dash, and t because you are evolving by time t. So you can say that it's the position space representation of this operator, of this evolution operator. And this is just psi of x dash, and you are integrating over dx dash to get your wave function at any given position x at a later time t. So you do this kind of an integration. So this is a kernel, and you integrate it with this fiducial variable. You take your wave function at a starting time, integrate it with this kernel to get the wave function at a later time. And you can compute this kernel once and for all. It's just this object. How can you compute it? Well, let me introduce another identity. Why I did it? Because I know the action of H on these. These guys are eigenvectors of H. I don't know how does this H acts on X dash, but I know how it acts on these K vectors. So this just gives me this X on it and picks up is P square over 2M. So H bar square, K square over 2M H bar. And then I get the K back. And this is now just a number. So it comes out. This guy is e to the iota kx. This guy is e to the minus iota kx dash. So it's just this integral. Well, 1/8 goes away. 2m, and then you have e to the minus iota, or let's say plus iota x minus x dash. Now this is a easy enough integral because it's a Gaussian. You can complete square and do it. I'm not going to do it for you over here, but let me just write the answer. Well, I think there was 1 over under root 2 pi coming from here, and a 1 over under root 2 pi coming from here. So there's a 2 pi here, but the final answer looks like this. This position space representation of the evolution operator for free particle is also called the propagator. Propagator in the sense it takes your function at time is equal to 0, and when you integrate it with this propagator, it leaves it at time t. And if you want it to be, you can derive it, not hard to argue. If I went from time 0 to t. If you went from time t naught to t, you will get exactly the same answer, except everywhere where you have a t, you get a difference of t and t naught. Makes sense because everything is time translation invariant. Now, using this, you can evolve any wave function. For example, I had the Gaussian. I take my state, that's my particle, free particle. No, it's not any particle, it's the free particle, which is in a Gaussian wave function at t is equal to 0. So my wave function is something of this form. Let's say x square, let me write it as 2 sigma square. Then by normalization, I will have pi sigma square 1 by 4. We had done this last time. If I, instead of this, if I consider this, E iota k naught x. It doesn't change the character of the Gaussian because you have x square and you are adding something to it. You can still write it as a Gaussian by completing the square. And moreover, when I make psi mod square, it's a different function. This function is different from this, but the positions probabilities, they are same. Because for both of them, you get this for the probability of position, because this guy drops out when you do the psi mod square. So this doesn't affect the position. Both are describing this probability distribution with certain sigma. However, if I compute I knew we did it last time that when I find out these guys, the momentum space wave function, they went something like, now I don't know the constants exactly, but it would be something related like this, something proportional to this, and some constants here, constants like 2 or 4 or something like that. So in other words, when I Fourier transform a Gaussian, I get back a Gaussian, but with the width inverted. That's all I'm saying. But this Gaussian we get from here is centered at k is equal to 0. So the average, so the probabilities of the k's, and which are proportional to the probabilities of the momenta, they are symmetrically centered around p is equal to 0. So that means the average value of momentum will turn out to be 0. And for that, you will have to do a Fourier transform, but you don't really have to do it because there's another way of computing the average, doing this. And I can, instead of writing all the bars and cats introducing the identities, I can directly work in the position space. And in the position space, what happens? P becomes d by dx. That's the operator for P in the position basis. Psi is represented by the wave function. Ket bra psi is represented by the conjugated wave function. And this bracket, the scalar product, is just this. So these are the rules. We have discussed them, but I don't know, we go fast, so I just keep repeating. But just remember this, that's the rule. In position basis or in momentum basis, any basis you work in, you will have a representation of the operator. So in the position basis, representation of P is this. And the scalar product will be some kind of a integral. So this, when I do it for psi of x, when this psi of x is this Gaussian, this one, then it's obvious when d by dx will act on it, it will bring down a 2x. 2x and a Gaussian here and a Gaussian here. So it becomes 2x times some Gaussian. And since it's this is even and this is odd, so you don't have to compute anything. The answer is going to be 0. On the other hand, if I act on this guy, where you have this Gaussian, I'm just leaving out the constants. E to the iota, e to the minus iota k naught x, e to the minus x square over 2 sigma square e to the iota k naught x. So when this derivative x on this guy, it again brings down 2x. These two cancel, and that integral gives you 0. But this derivative can also, then in the next turn, it will act on this and leave this as it is. And when that happens, these two guys still cancel. You get this back, the Gaussian, and from here you get minus iota times iota, which gives you 1. So you get h by k naught. And since this Gaussian was with your particular normalization normalized, this gives you 1, and you get this average value for the momentum. So whatever wave number you had attached to it, this is not a pure wave. This is a summation of many, many waves. If you will make the Fourier transform, you will get a thing like this. You will still get a thing like this with all these wave numbers are present. But this time, because of this average, you know that they will be centered around k naught, not around 0. So by attaching this guy, you are now considering a wave packet. Well, these Gaussians, which are compact waves, looking like a compact thing, people call them wave packet as well. So this wave packet is in an average sense moving to the right. But how exactly it is moving to the right? For that, we have this formula. Take this evolution kernel, multiply it with your desired Gaussian, and integrate. So that's what you are writing. Dx dash, write that kernel, this guy, I'm not going to write it. I'm not even going to write it. Write that and then take your Gaussian, because I'm trying to see how does this Gaussian moves. And there are some constants as well coming from the normalization of this Gaussian. This kernel, what has it got? It's again a Gaussian kind of a thing. It's a e to the x square. I don't care what is the constant in front of it. As long as it's a e to the alpha x square, my formula for the integration of the Gaussian does work. So I can use my Gaussian integration formula, or if you don't remember, just go to Wolfram alpha and do it from there. In this case, you get kind of a mess. I'm just copying it, what I had calculated before. Minus half e to the minus delta square times this is the wave function you get. And the first thing to note about it,
सर ये डेल्टा क्या है?
delta is just controlling the width. ये मैंने यहाँ पे डाला था. Sorry, delta is two yeah, sigma. So one thing you can see that it is still a Gaussian in X. So when I'll compute the probability of position at a later time, this drops out. and I get some kind of a Gaussian for the probability distribution as well, because it's a x minus. But this is now not centered at 0. My original probability was centered at 0, like over here. It has moved. It has moved by P naught, whatever P naught is, h bar k naught, your central momentum. So it has moved by P naught over m times t. And what is P naught by m? Classically thinking, P naught is just mv. So it's vt. So in a sense, in an average sense, this Gaussian was moving to the right with the speed given by this momentum P naught. So it has, its center has shifted by that amount. So it has gone here, depending on how much time it had got. So with that time, with this speed v, it has moved.
Excuse me, sir.
Yeah.
Sir, आप बार-बार repeat कर रहे हैं that it's moving to the right, so it's like it can't move to the left, or या फिर मतलब
What do you mean?
positive?
It can move to the left if I had put in, why was it moving to the right? Just because I had put in this guy. So if I had put in this guy,
Negative, okay.
yeah, then it will move to the left. Because this minus, because what is P naught? It's just K naught over H bar. So this will be replaced by plus. This minus over here will be replaced by plus. So it will then have shifted to the left. But not only that, if I compute psi mod square, which is again, you need to do some work, not gonna waste time. You get some mess here, but not that much of a mess as in the last expression. This is sigma. And exponent over m square and divided by sigma square plus h bar square t square over m sigma square. So what you see, you had a width of it over here. So whatever is coming down, sigma square, is its standard deviation. That standard deviation is increasing with time. If you give it more time, that standard deviation increases. So you started with this. With time, it moves to the next, but it's not the same Gaussian now. It's a spread out Gaussian. And if you wait more, it will move more over here, but it will be spread even more. So this wave packet is a very important property of these free particle, that the wave packet, if you make a wave packet, you give it time, it just doesn't move, it spreads out. And it spreads out, one can trace this spreading out to the fact when I make a wave packet, I'm adding many Fourier pieces, right? So those Fourier pieces, because of this relation, this dispersion relation, all these Fourier pieces are moving with different speeds. So if you kind of think a little bit classically, sometimes it's just helpful. It's not like strictly part of the theory, but it helps in thinking. Then you can derive a speed from here for any given k. right? So half mv square h bar square k square over 2m. I have used some part to give my quantum expression, and I have used this v, so you can derive the expression for v. And the speed depends on, is kind of proportional to k. So each wave moves with a different speed. Well, you can also do this whole analysis by looking at their phase speeds, the phase velocity of these waves, and you will just find out that each one of them is having a different speed. So whatever initial superposition you were making, that gets disturbed. So because of that, it spreads out. While if they were all moving with same speed, then it won't spread out. So this is a property, this is coming because of this dispersion relation. For the case of, well, let me move ahead. If you kind of have seen this formula, then energy is h bar times the angular frequency, and p square over 2m gives you h bar square k square over 2m. So from the angular frequency and the wave number, you can derive their speed. So speed is omega over k. And you find that each wave is moving with a different speed. Each k wave is moving with a different speed. While this does not happen for the case of light. So if you make a wave packet of photons, for them, this will not be true because this is a non-relativistic expression. When energy is equal to p square over 2m. We know that in relativity, the correct expression should be p square plus m square. So for photons, where this is 0, E is just equal to p. So that gives me h bar omega is equal to h bar k. So omega is equal to k. So omega over k is equal to c, and that becomes a constant because for each case, this is omega, since omega is equal to k, so omega over k is just a constant. So I can put it over here. V always comes out to be k over k equal to 1, as it should be for light. While in this case, V is coming out to be, I can use this expression equating these two equal. Omega is equal to h bar k square over 2m. So h bar k over 2m. So each wave number has a different speed in non-relativistic case, while for the relativistic case, relativistic massless particles like a photon, the speeds are, they do not change. So for them, the wave packet will not disperse. But for these non-relativistic, which we are discussing right now, the wave packet disperses. So this is a, like, it's not just that. So if, what does it mean? It means if I confine an electron, somehow I know that the electron is within this distance. So maybe you guess that probably some kind of a Gaussian within this region, and maybe you have taken much care to make it a Gaussian, because Gaussian gives you like a tightly packed probability in this small region. And you wait for some time. This will move, but your localization, and how had you localized it? Even if you had measured it, if you had measured its position and your result was x naught, obviously your instruments are never going to give you exact same value. Your instruments have a certain level of, this is not quantum mechanical, this is just practically speaking, experimentally speaking, your instruments will have a certain precision level. So some margin of error, because you measure within, like, you cannot say it's 0.123 and keep going. You say it's 0.123. Beyond that, I don't know. It's some number around it. So you make a small interval and you say that I have localized over here. So you are sure that at this moment the electron is here. It's localized within your precision of measurement. If you wait for some time, it spreads out. It doesn't remain localized with the same precision. It becomes delocalized. You wait more, it becomes even more and more delocalized, and finally the probability just spreads out completely. It's not just the property of the Gaussian. You can try anything, any kind of a wave function here. It always happens that it spreads out. So any question? But what is important is that this is a property of free particles. So if we have, for example, an atom where we say that the electron is within the small region, the size of atom, what does it even mean that this is the size of atom? That means the electron is localized here. It would be found within this region. So that means it's not getting delocalized with time. So how come that's not happening? The forces come into play. You need some kind of a forces, some kind of force to stop this tendency of the particles, at least non-relativistic particles, to spread away. Any question? You can check that even if I hadn't included this thing, this I put in just to give it a push to the right. Even if this was not there, then that would mean its average speed is 0. And by the way, this is just the average speed. And average speed doesn't mean that the electron has different speeds and this is the average. It just means that there's a probability for the different speeds, for different momenta. If I measure the momentum of this electron, I can get any value. I can even get it that it's moving to the left, if that is within the allowed values. So let's say this is k naught, and depending on, this is 0, k is equal to 0. Depending on the width, if there's appreciable probability over here, then if I measure the momentum or speed of this particle, there's a probability that I'll find it to be moving to the left, to the, which one is right? So to the left even. So this is just the center of the probability distribution. That's all what I mean by average speed. It's not the average of anything. It's the average of average only in this sense that if I have a million electrons, million particles, all in exactly the same state, and if I start making measurements on them, they will all give me different speeds. I compute the arithmetic mean, that would be this average. So just usual probabilistic concepts. So even if I hadn't included this, then the average speed would be 0. This would be the starting distribution of momenta. And then the wave function, you will find out that the wave function doesn't move. Its center doesn't move because the average speed is 0, but it still spreads out. So with time, the center remains there, but the spreading, this factor, you can notice it, k0 does not appear here. It has nothing to do with it. So it still spreads out and you cannot do anything about it. Now, let's now consider some other.
सर इस बात की फिजिकल मीनिंग क्या होगी फिर कि क्यों स्प्रेड
It's just, I mean, this is a fact about waves. It's just a Fourier property. It's just coming from this fact that energy is related to momentum. Well, energy is related to momentum to this expression, so that the speeds of different wave numbers are different. And it's just then a Fourier fact that if you make a wave packet out of these Fourier components, and then the way these Fourier components oscillate is correlated in a particular way. They're not going in sync with each other. So the wave packet cannot maintain its shape. It does something weird because they all are oscillating out of phase with each other. And what happens is that it spreads, because that's what we have explicitly proved. And you can explain this spreading to another means. So you have a range of momenta possible. This is the K space. And in X space, you have this wave function. So I can find this particle here, 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 here. All these things are possible. But after some time, this guy, because all these momenta are possible, it's possible to land here because of, let's say, this momenta. But it's also possible to land here because of the next momenta, and possible to land here. Similarly, this guy has a probability of landing at different values. So because of this spread in momenta, what happens is that all these possibilities, they do not get shifted. So you can imagine that if there were only one momentum possible, then all these values will just get shifted like that. But right now, each of these particles has many different possibilities of momenta. So this whole range gets even more spread out. So it's in a sense a consequence. One shouldn't say consequence. In terms of thinking, you can say it's a consequence of uncertainty principle. But at a deeper level, uncertainty principle is just a consequence of Fourier. Uncertainty principle is just a physical interpretation of what the waves are doing. So this spreading of the wave packets, this has nothing to do with quantum mechanics. This happens if you have these kinds of waves with this kind of dispersion relation, where omega, if I have let's call it some constant. If you have this kind of dispersion relation, this relation between wave number is just inverse of wavelength, and the angular frequency is just how many times it waves. If you stand at a point, how many times it waves in a second, while this wave number means that within a meter how many wavelengths you can fit in. So if the relation is like this, omega is proportional to k square, then this kind of wave is going to spread. It's just like you make, if actually the waves in water pond, they are of this kind as well. If you make a lump in water, throw in a stone, you create a lump, it doesn't stay like that. It spreads away, it dies down. While if you have this kind of relation, linear relation between frequency and wave number, then if you had created a lump, it will move. That allows for the laser, that is true for the light, and that allows for the functioning of lasers as well. So it's just a fact about waves. What quantum mechanics does is it gives an interpretation to these wave numbers and these frequencies. So what is this wave number? It relates it to momentum. And the spreading, it relates it to the probability of positions. So it just says that your position or where you find it, that's spreading out. So waves, ordinary waves, they are just waves. This is also a wave, but this wave has a particular meaning. This wave is not a physical wave. You cannot touch it, you cannot smell it, you cannot detect it. This wave is just there to give you probabilities. Its square gives you the probabilities of position, but you do not always have to square it. You do not square it, and then you can extract other probabilities from this wave. So this wave is a wave which contains all the probabilities for you, and it's just a mathematical abstract thing. It does move in real space in the sense that you can describe its dynamics, and depending on the mental picture which you have in your mind that what this wave is doing in space time, you can extract probabilities, but you cannot touch it, you cannot detect it. So the wave function is not like a field. It's not electric field, it's not light, it's nothing of that sort. It's just a mathematical object. It exists in the space, but it's not real in the sense that you cannot detect it. You can only get probabilities out of it, and the measurable things are probabilities. Now, let's make some general remarks, because now I'm going to consider some other systems. So you have some potential. So that's what we decided, that to describe any particle moving in normal kinds of forces, I'm gonna pick up the potential which gives me that force and create this operator, and that will describe for me the dynamics. And we have also discussed it. To get the dynamics, I need the energy eigenvectors. If you know this, why do I need it? Because when I compute the action of the evolution operator, I just bring in this identity, and then I know how the action works, because it just picks up E, and then I can work with it. So you have to solve this eigenvalue problem. And as we had discussed, that this eigenvalue problem when written in position basis. So in position basis, this energy eigenvector will be a function. So let's call it psi e of x. And this h is just these operators. So it would be p square over 2m would be the square of p, which becomes minus h bar square over 2m d2 by dx square, because p is minus iota h by d by dx. So this gives you this, and then h becomes, and v of x is just, you take the functional form of your potential, and since in the position basis the x operator just acts like a multiplication with the variable x, so you just take the functional form, classical functional form of your potential. For example, if a particle is moving near the earth, the potential can be taken to be mg x, where x is this height variable. So then the operator would be just mgx. So your total Hamiltonian in the position basis becomes plus v of x. And what will give you the dynamics is this equation. And this equation in the position basis then looks like this. Psi e of x, because this Hamiltonian is acting on this e, which in position basis looks like psi e of x, and it produces e psi e of x. So that's the eigenvalue equation translated to the position basis. You should be able to, you should do it, derive it by bringing these kinds of things. I've done it so many times that I'm not going to repeat these, but you guys should definitely try it. So you get this equation. And this, as I had also called, discussed before, this is called the time independent Schrödinger equation. Just a historical name. But what it actually is just an ordinary. I am just used to writing a partial. We are only in one dimension. If you are in more than one dimensions, then it becomes a two partial differential equations. But for now, it's just an ordinary second order differential equation. And you can try to solve it using your favorite methods of solving differential equations. But this kind of equation where you have this particular form is called Sturm-Liouville problem. We don't need to discuss this Sturm-Liouville problem in complete generality right now. Probably I'll do it at some later point. But the thing which I should just mention over here is that in Sturm-Liouville problems, many a times the problem is such that you cannot take this as not a fixed constant. So if you take this as a fixed constant and pick any constant, many a times what happens, well, many a times what will happen is that you will not have no solution to your equation. So in a sense, you are solving for this constant and the function at the same time. For specific, many a times, not always, many a times there's a solution for all values of this constant. But sometimes for some special forms of these, it may happen that you have a solution only for very specific, actually a discrete set of values of this constant E, you will have a solution. So this is just like solving the eigenvalue problem. So Sturm-Liouville problem is a generalization of matrix problem. So when you have a matrix eigenvalue equation, you solve for both eigenvalues and the corresponding eigenvectors. So similarly here, this thing is an eigenvalue. So you solve for it and you solve for corresponding eigenfunction. Now, for these eigenfunctions, and by the way, these eigenfunctions, they are, I can think of this thing. This is how actually I got it. So they are, since they are eigenfunctions of Hamiltonian, so they form a complete set. So even if I get a discrete set, it will be a complete set. Many times what would happen, you will have some discrete part and some continuous part, but whatever set I get is a complete set. So for example, for the case of this Hamiltonian, I saw that this was the eigenfunctions. In this case, energy was not discrete, but that's okay. But these eigenfunctions formed a complete set because these are, I can expand any square integrable function in terms of its Fourier components. So it is, in fact, a complete set. So the general Sturm-Liouville theory tells me, and we have kind of discussed it, at least kind of tried to argue that this Hamiltonian sense in our special L2 space with these extra functions, since it remains a Hermitian operator, so its eigenfunctions must form a complete set, and that's what Sturm-Liouville theory proves in a little bit more detail. So any set of eigenfunctions you will get from here will be a complete set. That would mean that you should be able to write all your functions these are special. These are eigenfunctions of energy. But any wave function, people get confused. Well, not people. Some students who are learning for the first time, they get confused between energy eigenfunctions and the wave function of a system. So since most of the time people start just solving for the energy eigenfunctions, they think like particles exist only in energy eigenfunctions. That's completely wrong. Particle can have any wave function to start with. All you say is that any wave function which particle can exist in, any wave function in principle can describe the state of the particle, but you are able to expand that state in terms of energy eigenfunctions. That's all you have. It's not that you have energy eigenfunctions and particles only exist in energy eigenfunctions. But looking at this equation, I can also write it. Let me try to write it over here. d2 psi by dx square is equal to E minus V of x and minus 2m over h bar square psi of x. This is the differential equation. And it's not one differential equation. You change the v of x, you get a new differential equation. And our problem is to solve these differential equations for different v of x. And only a few exact solutions can be found, but obviously there's a huge technology to solve these numerically. But looking at this, I can make some statements about continuity. Well, this is psi of E. Continuity requirements on psi of x, psi E of x. So this v of x mostly is a continuous function. Mostly, I should say, in principle, always. Because remember, force is a derivative of it. So if it has a discontinuity, you will have an infinite force at that point in space. So you have a potential. If it takes a jump, this potential is changing from point to point, and depending on this, how this changes, you have a force acting in different directions, classically speaking. But if you have a jump, then you have an infinite derivative. So you have an infinite force, which is obviously not possible. So in principle, this potential is always continuous. But we will be, for our simplification, we will consider discontinuity in the potentials because things are easier to describe. Some systems are easier to describe with discontinuities. And you just think of it as a very large force. That's it. That's the main idea. And but if I consider it to be continuous, which would actually be the case for real systems, then I can look at over here. What does it tell me? It tells me that d psi by dx square, I cannot take, if psi is discontinuous. Suppose if psi is discontinuous, what would happen? At some points, d psi over dx will not exist at points of discontinuity. And actually, I should think of it that it becomes infinite because I have a, if you have psi breaks up. So d psi by dx gives you an infinite jump. So rate of change becomes infinite at a point. What is wrong with that? Well, what is wrong is that if it becomes infinite, you cannot make the second derivative. So this equation loses meaning. So a discontinuous psi cannot solve this equation because you cannot even construct this operator over here. So conclusion is that psi E of x is always continuous. And if psi E of x is continuous, what is this guy? This is just a linear combination of these continuous functions. So any wave function you consider will be continuous. There's no other choice. All wave functions are continuous. That's a basic requirement. Slightly stronger than the fact that you had square integrable functions. So all these are psi e of x are always continuous. But if that is true, then this guy minus, what was it, 2m over h square, this is continuous, this is continuous. So that means left hand side, the second derivative is continuous. So that means the first derivative has to be continuous too at each point. So that means psi, psi dash, and psi double dash are all continuous. However, I will consider situations where for purposes of ease of calculation, we consider potentials that have jumps. So for example, I can consider a system, potential is constant, drops like this. This is called a box. And you can literally think like if you are considering a gravitational system, this is literally kind of a hole in the ground. You are here, you have lower potential energy. Here you have a other constant, but this value is constant. Let's say call this constant 0. Then you have a higher potential energy over here. Or this is the ground, this is the a building, the ceiling of the building. If this wall is straight, then you have a jump in potential. And you can describe many systems like this. Obviously, it's not a strict jump. In principle, it's like this. It's not like a very strict jump, but you don't want to deal with this kind of thing. This is much easier to model. And as a physical system, you can literally think of like a particle which is sitting on the road and then is surrounded by these flat top buildings. And you can also think of like one-dimensional atoms. So it's trapped inside. Whenever you want to approximately describe a particle trapped somewhere, so it could be sitting in this kind of a potential. So to get over here, it needs some energy. There's some energy here. Let's say it's not moving. In that case, energy is 0. Or maybe it's moving. So it has some energy E, but let's say if it's less than V naught, then it cannot go out unless you provide it this difference. So you can model trapped particles by this kind of potential. So if you have a jump like this in potential, then what would happen? I come over here on the right hand side in this function, let's call it some function f of x, you have a discontinuity. So that means d2 psi over dx square will be discontinuous. However, if you have a discontinuity, because why you have a discontinuity? Because you have a finite jump in V with a finite jump. So it's going like this. और जो भी इसकी वैल्यू ऐसे going like this. But if there's a finite jump in d2 psi over dx square, it only means d psi over dx has a kink. आपके पास अगर ऐसे है, let me know. यहाँ पे आपका ये है d psi by dx. और इसका जो rate of change है d2 psi by dx square, it was changing continuously. मगर यहाँ पे d psi by dx ने एकदम turn लिया. So your derivative of it, rate of change, took a jump. That's what gave you this difference. So it would mean that d psi by dx has a kink, but it is still continuous. So, or you can argue it this way as well. So ये है ना d2 psi by dx square was equal to some function f of x, and this has a discontinuity. So let's write it like this. So d psi by dx is the integral over here. So d psi by dx, so this f of x I'm plotting, and it has a jump. D psi by dx is the area under it, because the integral. So even if you have a finite jump, as you go from here to there, as you move, the area still takes continuous increments. You're just adding another strip. So d psi by dx still remains continuous if you have a finite jump. So if f of x has finite jumps, its integral is still continuous. So the conclusion is that even if you have jumps in your potential, your psi e of x and psi e first derivative of x will still be continuous. You cannot say anything about, well, you know that psi double dash will not be continuous, but these two will be continuous. So we will use this fact when I will solve some system like these, then this information will come handy, that even though I have a jump here, but I must still demand these two continuities. I think we should stop here, and I'll come tomorrow again at 3, and it's up to you if you want to join me. I would appreciate if you do.
ओके सर। सर वो एक रिक्वेस्ट थी कि आप ये स्लाइड्स भी हमारे साथ अगर शेयर कर दें,
हाँ
जिससे
ठीक है,
आप
मैं
नोट
इनका प्रिंट आउट करके ना, आज तो नहीं मैं कर सकूँगा, आज मुझे बहुत काम है, कल मैं ये करके ये मैं आपको भेज दूंगा।
और
थैंक
सर
यू
आपने
सर, थैंक
पिछला
यू।
लेक्चर भी अपलोड करना है।
इसलिए नहीं
और
हुआ अपलोड?
नहीं, आप भूल
नो
जाते हैं।
सर।
ओके चले, मैं वो करता हूँ। आई थॉट अब मैंने कर दिया है, मैं भूल गया। ओके